to short text 331. Today we're going to talk about linear operators, and this is going to be part one of what's probably going to be a 2 or maybe 3-part subseries on linear operators. So we define a linear operator as a mapping between two vector spaces. We're going to call the mapping A here, and the two vector spaces V and W. And that mapping, to be linear, to be called a linear operator, has to satisfy these two properties, which are of course linearity. If you apply the operator to the sum of two vectors, v1 and v2, in your vector space, then you have to get the sum of the results of applying a to v1 and a to v2. And if you apply your operator to a vector that is a product of a constant times a vector, then that constant goes right through the operator, and the result is the constant times the operator applied to your vector. And here in this case, the vector is just v. If you have these two properties, then you have a linear operator. And of course, a very simple example of that is a matrix that I call here A with components 1, 2, 3, and 4. It's a mapping between the real numbers with the two component vectors with real entries and itself. So it's a mapping from R2 to R2. And indeed, if you apply your matrix A to a two component vector AB, then you get this result: A plus 2B and 3A plus 4B. That is a vector in our target space, which is W, which is R2. Of course, these two components are both real, and no problem there. And if you apply A to the sum of two vectors, you can easily see that you get the sum of applying the vector to the transformation, the operator to both vectors individually, and then summing the result at the end. So let's take a look. So if I sum these two guys, x1, x2, y1, y2, I get this vector, x1 plus y1, x2 plus y2. Now I will apply A after that, and so I get this x1 plus y2, y1 plus 2, x2 plus y2. That's basically what we have here, A plus 2b, where A is this component and B is the other component. And then the same at the bottom, 3, x1 plus y1 plus 4, x2 plus y2. Now I can separate the x's and the y's by doing this, by taking x1 and 2x2 and putting it to the top component of a vector, and then I can put the 3x1 and the 4x2 down here in the second component of the vector, and then I can separate the y's in the same way into another vector. So the sum of these two vectors is of course equal to this big vector here. There's no issues there. But then I can see that this guy is actually the same as applying A to x1, x2, and then this guy here is the same as applying A to y1, y2, and therefore you see that indeed A is a linear operator in that sense. So A applied to the sum is the same as A applied to the two individual vectors and then summing the result at the end. And everything works out in the same way regarding the second property, multiplying by a constant. Is very easy to see that the constant goes right through the operator, and there are no issues there. In fact, all matrices are linear operators, and we'll see more about this soon. Now, another linear operator that you've worked with many times, and perhaps you didn't realize it's a linear operator, is the derivative operator. So ddx, this derivative operator, is a linear operator. And indeed, you know that the derivative of the sum of two functions is the sum of the derivatives, and the derivative of a constant times a function is a constant times the derivative of the function. And so you see right away that the derivative is indeed a linear operator. If you enjoyed this video, if you like this series, please like and subscribe. If you're looking for a tutor in physics or math, in English or in Spanish, you can contact me at shorttext331@gmail.com, or you can leave a message in the comment section below. Now, remember that we talked before about vectors being abstract entities. So I said in a previous video, actually many videos ago, you can look at the one of the first few videos on vector spaces and definitions and examples of vectors, that vectors have life of their own. So vectors are abstract entities. So when we write v is equal to 1, 2 like this, what we're really saying is that 1 and 2 are the components in this basis, the canonical basis 1, 0, 0, 1. Because what we're saying when we write this is really that the vector is 1 times 1, 0 plus 2 times 0, 1. This is really what we mean. Now, if we change our basis, we will get a different representation. So if we change our basis, then our vector will really be, will take some other form. For example, if we pick a basis of vectors 1 half, 1 half, 1 half minus 1 half, like we see here, then our vector is really going to be 3 and minus 1. Those are going to be the components of the vector in that other basis. So this way of representing a vector with components really depends on what basis you're talking about. So a vector otherwise has a life of its own. So you have to say these are the components. Well, in which basis? So usually when we write like this, we mean in this canonical basis, but we could also be referring to a different basis. And so it's important to say which basis are you in. And it's the same for linear operators. Linear operators are represented by matrices in the same way that vectors are represented by n tuples like this. The columns or rows of numbers, and in the case of linear operators, it would be a matrix, and once you fix the basis, then that matrix will be fixed. And so, for example, if our vector space V is a space generated by linear combinations of 1, x, and x squared, we can try to find a representation of the derivative operator. And so in this space, then the vectors will take the form constant plus another constant times x plus another constant times x squared. So a plus bx plus cx squared. So it's a space of polynomials of degree 2 or less. If c is 0, then I have a polynomial of degree 1. And if b and c are 0, then I have a polynomial of degree 0. And so these a, b, c coefficients are the coordinates of my function of my polynomial in this basis 1x x squared. Now you can go to that basis and apply our operator to that to each of the components of that basis. So if I take the derivative of 1, I get 0. And so the 0 vector in my space is basically the vector with component 0, 0, 0. I have to put all a, b, and c to 0 if I want to get 0 as a result of this. Now if I apply my derivative operator to x, the next component of my basis, then I get 1. The derivative of x is 1. And so that is just a constant. There's no x dependence in the result. And so the components of that, a, b, c, d, are 1, 0, and 0. So that's the column vector that represents the result of applying a to x. Now, what is the result of applying a to x squared? Well, if I differentiate x squared, I get 2x. And so 2x means that b would be 2, but a and c would be 0. And so that's what I wrote here. I wrote 0, 2, 0. And then you take these results in columns and you assemble them together into a matrix. And this would be finally the matrix representation of the derivative operator in this basis. You probably never thought about it this way unless you've seen this kind of stuff before, but the derivative operator can be thought of as a matrix as long as you fix the basis. And this is the case here. This is our matrix representation. And this makes sense. Suppose that we have a vector in our space that takes this form, a plus bx plus cx squared, and is represented in this by this coordinate. And then we apply the derivative operator by applying that matrix to our vector. What do we get? Well, we take our matrix, we apply to a vector, and you see we get 0, 1, 0 applied to ABC, we get B for the first component. 0, 0, 2 applied to ABC, we get 2C for our second component. And then 0, 0, 0 applied to anything you want is 0. And so you see the result of applying the derivative to a plus bx plus cx squared is b plus 2cx, which is indeed the correct result. If I differentiate this vector, I get b, and then the x disappears, and I get 2c, and then I get, instead of x squared, just x. That's what differentiating means. And so you see, this worked very, very well because indeed, the derivative is a linear operator. And so taking a derivative is the same as applying a matrix to your vector once you pick the basis. Now, to solve problems, ax equals b for a given operator, whether the operator is a matrix or whether your operator is a differential operator, it's useful to understand other properties of operators, not just their matrix representation, but more general properties. One thing that we want to know for sure is, does the inverse of the operator exist? Can I put this operator on the other side of the equation? It's b in the set of possible results. So in other words, if I need to find the x such that when I apply a to x, I get b, b must be in the possible set of results that I can get from applying a to anything. That's what we call the image of a function typically. Is it in the set of target result? So that's what we call the image of the operator. So we want to know what that looks like, the image of a. What does it look like? And so I have a diagram here showing the schematically what's going on. So we have our vector space with all the vectors to which we can apply a. And once you apply a, you obtain a vector in the target space w. Now within w, there will be a subset here, which is the image of a, which is all the vectors that are mapped onto by a. So once you have your set of vectors here, you pick a vector, any vector, you pick all possible vectors of v, and then you apply a to them, and you get this subset image of a. Now the 0, of course, the vector space always has a 0, so the 0 is always mapped onto 0, by a linear operator, it's very easy to see that all linear operators map 0 onto 0, because indeed if you have a times x, you can write x as x plus 0, and then the operator can be applied to the sum, but it can also be applied individually, and then you can sum the result at the end, and that's what I did here. So we get that the result of this is a applied to x plus a applied to 0, but x appears on both sides of the equation, and that tells us that a0 is equal to 0. So the 0 here is always mapped onto 0. So the 0 is always in the target space, is always in the origin space or the domain, but it's always in the image of a, for sure. You always have 0. Now there may be more vectors that are mapped onto 0. That may be possible as well. And so that is a very important set of the domain. It's called the kernel. And so the kernel is the set of all possible x's, including the 0, of course, such that ax is equal to 0. So all this set here in green, which includes the 0, is mapped by a onto the 0 vector here, just the 0 vector. And then everything else is mapped generally onto somewhere on the image of a. And then maybe some other stuff left behind here in your bigger space. Now the question that we want to answer, the question that really matters to us when solving linear systems of equations, and this is a very important property of operators, is whether the inverse exists. So you have an operator that takes you from your space to another space, and if you want to solve a problem like this, ax equals b, then you want to know if it's possible to come back, if it's possible to apply the inverse and get some value of x from which that b comes. Okay, and that's would be given by an inverse, and this is a question that we want to answer. Now, this mapping between two vector spaces is a mapping in the same sense as a function, a regular function. That is to say, there's a vector, you apply some operations, and then you obtain another vector. With functions, you have a number, you apply the function to the number, you evaluate it, and you get another number. And you know that the inverse function exists if the function is 1 to 1. So if for every value in the result, there's only one value from the on the domain that gives you that one value in the target or in the image space, in the image set, then you know that you can look it up. You can look up where a given value came from. That is exactly what this function does. It tells you, given value here, I can tell you where it came from in the other set. That's the inverse function. And this is the same for operators. So if the inverse operator is to exist, is well defined, then you have to have that for each value on the image, there's only one value of x that will give you that result. And so you see right away that this kernel is telling us a little bit about this, because we already know from what we showed here that the 0 is always mapped on the 0. Now, if there's more values in the domain that are mapped onto the onto 0, then there's multiple values that I wouldn't know how to distinguish, because all I know is that they're mapped onto 0, and so I wouldn't know where to go back. I always know that the 0 goes to 0, but if there's more vectors that give me 0 as a result, then this inverse is not well defined. There will be, in a way, multiple inverses, and so that means that the inverse is not well defined. And so we already then can see that for an operator to have an inverse, it must be that the kernel is only the 0 vector. If an operator is to have an inverse, then the kernel must only be the 0 vector. And you see an example where this fails, right? Pretty much up here in the example that we saw before of the derivative operator. The derivative operator, no matter what this constant is, if it's 1 or 2 or 3, will always give you 0. And so the derivative maps 0 onto 0. Of course, the derivative of 0 is 0, but the derivative of 1 is also 0. The derivative of 7 is also 0. And so for us, if A is a derivative operator, then any object that is a constant will be in the kernel, and so will be mapped to 0 right away. And let's see if we can see that in the structure of the matrix. So you see a whole column of zeros here. So no matter what A is, if B and C are 0, then no matter what A is, that will always be mapped onto 0. So you see A doesn't even appear on the result. Yeah, so we applied the derivative to a generic vector, and no matter what A is, if B and C are 0, then this is always going to be 0. And this tells you then that the kernel is non-trivial. The kernel is not just a zero vector. There's more. There's more in that kernel. And so this derivative operator, as written there, doesn't have an inverse. So there are ways to build inverses of differential operators, and we will talk about that in a future video. But as we define it there, it doesn't have an inverse. So something needs to be done if we're going to fix that problem. All right, that's all I have for you for today and for this video. And if you enjoyed it, please like and subscribe. And if you're looking for a tutor, you can contact me at shorttakes331@gmail.com, or you can leave a comment in the comment section below and I'll get back to you. Until next time.